In the name of God, the most gracious, the most merciful, peace be upon you and God's blessing. We are going to have a look at practice problem number 5.1 from the Steel Design Handbook. In the built-up shape shown in figure 5.6, determine A, the elastic section modulus capital S and the yield moment M sub Y, B, the plastic section modulus Z and the plastic moment M sub P. Bending is about the x-axis and the steel is A572 grade 50. The overall height of the given section is 1 foot plus 2 inches, which can be expressed as 12 plus 2 equal to 14 inches. Due to symmetry, the elastic neutral axis will be located at the mid-height of the given section. The expression of the elastic section modulus capital S sub x is equal to Ix divided by Y max. Y max is measured from the elastic neutral axis to the top, which is equal to 7 inches. There are two ways to find the inertia Ix for the section. The first method is to consider the whole section inertia as composed of 3 rectangles. The first rectangle is the top rectangle for the upper flange, the second rectangle is the web section, and the third rectangle is the lower flange, and then estimate the inertia about the x-axis. The second method which we are using here is to estimate the inertia for the upper flange area and half of the web area about the x-axis, and then multiply by 2. In the next slide image, we can see the steps to estimate the inertia for the first rectangle, which is composed of 2 items, which are the value of 8 multiplied by 1 raised to the power of 3 divided by 12 about the CG, plus 8 by 1 by 6.5 to the power of 2. The value is 338.606 inch 4. While the inertia for the half of the web area can be expressed as B multiplied by T raised to the power of 3 divided by 3, where B is the base, T is the height of half of the web area, the value of Ix2 will be equal to 36 inch to the 4. Adding Ix1 plus Ix2 and then multiplying by 2, we will have Ix equals 749.33 inch 4. The value of the section modulus is equal to 749.33 divided by 7 equals 107.05 inch cubed. This is the first requirement in part A. We move to the next slide. Also in part A, it is required to find the M sub Y, or the yield moment value, which can be obtained by multiplying the value of F sub Y by S sub X. F sub Y is equal to 50 KSI, since we have A572 steel grade 50. The value of the elastic section modulus S sub X is 107.05. Multiply 50 by 107.05 will give 5352.6 inch kips, divided by 12 to get the value in foot kips. The final value of M sub Y is equal to 446 feet kips. There is another way to find the M sub Y from the first principles, as we calculate the compression force acting in each part. I mean the compression force C1 acting on the upper flange area, and C2, which is the compression force acting on the web area. We have the upper flange edge stress equals to F sub Y, which is 50 KSI. We need to find the value of the stress at the junction. The stress value at the junction equals 42.857 KSI. Now we have the data to estimate the two compression forces C1 and C2. the value of C1 will be equal to the value of the average stress by area, which will give 371.428 kips. The distance from the C1 force to the elastic neutral axis is 6.5 inches. Similarly, we can estimate the value of the force C2 by multiplying the average stress, which is equal to 1/2 of 42.857 by the area, which is equal to 3 inches square. The final value of C2 equals 64.285 kips. The distance from C2 force to the elastic neutral axis is 4 inches. In the next slide, we list the values of the compression force C1 and the YCT from C1 to T1. T1 is the tensile force, which is equal to C1. YCT is equal to 13 inches. The value of C2 is also listed with the value of T2, which is the tensile force acting below the neutral axis. The vertical distance between C2 and T2 equals 8 inches. We sum the products of forces by the neutral axis distances. We get the final value of M sub y, which is equal to 445.23 feet kips, which is close to our estimated value of M sub y. For part B, which is the value of the plastic section modulus Z sub x, we can find that the P.N.A, which stands for the plastic neutral axis, is located at the middle of the built-up section due to symmetry. We need to find the total area and then divide by 2. The total area equals the area of the 2 flanges and 1 web. The final value of the area is 22 inch square. Half of the area is equal to 11 inches square. Y1 is the distance from the CG of the top flange area to the P.N. axis. Y2 is the distance from the CG of the half of the web area to the P.N. axis. In the next slide, we will use the moment of areas about the plastic neutral axis, or the sum of A multiplied by Y. A1Y1 equals 8 by 6.5, while A2 by Y2 equals 3 by 3. The sum of AY divided by A1 plus A2 equals 5.545 inches. The Y bar distance is the distance from the point of application of the compression force to the P.N. axis. We have a similar Y bar below the P.N. axis for the tension force, and it has the same value of 5.545 inches. The Z sub x, or the plastic section modulus equation, is the sum of A1 by Y1 star plus A2 by Y2 star. Since A1 equals A2, adding together, we will find that Z sub x can be expressed as equal to A total over 2 by Y1 star plus Y2 star. Y1 star equal Y2 star equals Y bar, which we have estimated. Z of x equals 11 by 2 by 5.545 equals 122 inch cube. In the last slide, M sub B, or the plastic moment, can be obtained from the equation of F sub y, which is equal to mb over z sub x. The modification of the equation can lead to M sub b equals z sub x multiplied by f sub y. The value of M sub b equals 50 multiplied by 122. Divide by 12 to get the M sub b equals to 508 foot kips. we could use the expression of f sub y by a1 y1 star plus f sub y by a sub 2 by y2, and then divide by 12, which will give the same result. Thanks a lot, and see you in the next new video. God bless you all.